So those equations of 3D elasticity in all their glory can be simplified to two-dimensional situations in a few standard cases. You might be aware of this. The first is plane strain, where the body is very long in one direction, let's say the z direction, and then you can and the loading on the body is also invariant with z, so the loading does not depend on z. Then on any xy plane like this, on any xy plane, you can reduce this to a problem in plane strain where there is no, where you assume that plane cross sections remain plane, therefore uz displacements in the z direction are zero, and things don't vary in the z direction at all. No field stress strain displacement varies in the z direction. Del z of everything is zero. Then you can do this reduction in the strain displacement relationships first. So del z is 0, del z is 0, del z is 0. So these immediately fall off. Then uz is 0, so this falls off, this falls off as well. So these become zeros completely. Del x, del y, this remains with uh, del x remains for the fourth row. The third row vanishes, and then this is your truncated operator matrix L, not truncated, reduced operator matrix L. That gives you the relevant components of the strain. Now we need not deal with everything because this is 0, this is 0, and this is 0, so we will throw them out and deal with only epsilon xx, epsilon yy, and epsilon xy. Similarly, we will deal with sigma xx, sigma yy, sigma xy, though as you might be aware, sigma zz is not necessarily equal to 0, but it is not independent anymore. It is dependent on sigma xx and sigma yy. So we will deal with it later. We will deal with sigma zz later, but first we will just write equations with xx, yy, and xy. Why is this a 2D problem? Because if you look from here on the xy plane, you can draw all these three components of stress or strain. So you can draw sigma xx, sigma yy, and sigma xy all on the xy plane. So this is a planar situation. Of course, you have out of plane stress sigma zz in this direction, but as I said, it's not independent. And if you know sigma xx and yy, you can find sigma zz. So now, after having reduced this strain displacement relationship, now we will look at the constitutive equation. So sigma xx, sigma yy, sigma xy, they are related to the strains. So I am trying to write sigma ij equal to Cij KL epsilon KL, this tensorial notation in Voigt notation under the situation that everything except xx, yy, and xy strains are 0. That's what our assumptions tell us. So sigma xx will be related to C1111 epsilon 11, 1122 epsilon 22, and then 1112 epsilon 12 and 1121 epsilon 21, both of which are equal and leads to this term. So again, yy will have 2211, 2222, and 2212. xy will have 1211, 1222, and 1212. So these are the only terms. Sigma zz will also be there, but you can easily show that sigma zz is actually a combination of sigma xx and sigma yy. Now in the isotropic case, we know this is lambda plus 2 mu, this is lambda plus 2 mu, this one is mu, this one is uh, 0, and this guy is lambda, this guy is lambda. So now you convert these things into you convert this into E and nu terms, and this is the stress strain relationship that you will get in case of plane strain for an isotropic material. And this form is quite famous, quite well known, and we will use it quite often. Similarly, you might be aware of the plane stress situation where the loading on this plate whose thickness in the z direction is small compared to its dimensions in the xy plane. For this plane, the loading is all in the xy plane. So the loads have no z component. In that situation, this is a traction-free surface. This is a traction-free surface. This normal is 0, 0, 1, and therefore on this, since the tractions are 0, sigma zz equal to sigma zx equal to sigma zy equal to 0. So sigma zz is 0 on this plane, and since this is thin, we assume that sigma zz is equal to 0 everywhere in the volume of this body. And we use that's a plane stress assumption, depends on thinness of this body. So we write sigma xx as epsilon xx, epsilon yy, epsilon zz, and epsilon xy. We have epsilon zz here because now it's plane stress. Epsilon zz is non-zero, can be non-zero, but sigma zz is not. Whereas in plane strain, epsilon zz was 0 and epsilon sigma zz was not. So we write sigma xx. Again, these 2's come because you have xy and yx both clubbed into this term. We write it for yy, we write it for xy. Again, this is for isotropic equal to lambda plus 2 mu. This is for isotropic lambda. This is for isotropic lambda. This is for isotropic 0, and so on. So this is also lambda. This is lambda plus 2 mu. This is lambda, so on. And then you finally write the one for sigma zz. We know that sigma zz equal to 0 because these surfaces are traction free. If sigma zz equal to 0, we have sigma zz equal to zz epsilon xx, zz epsilon yy, and so on. So this is equal to 0. So this gives us an equation from which I can determine epsilon zz in terms of xx, yy, and xy, plug it back into these equations, get rid of epsilon zz from here. Then, just like in the plane strain case, I have a relation connecting xx, yy, xy stresses to epsilon xx, epsilon yy, and 2 epsilon xy strains, and that matrix connecting them is this. So both in the plane strain and in the plane strain case, I try to determine these 3 components of stress as a function of these 3 components of strain. In both the cases, that's what I do. Only thing that changes is the 3 cross 3 matrix connecting them. You can, in the plane stress case, you can determine epsilon zz as a post-processing step. In the other case, you can determine sigma zz as a post-processing step. But what is processed, what is solved is this. And very often, a plane stress program and a plane strain program are written in one go, in one body of code. Only change is a small if statement that triggers this stiffness matrix in case of plane stress and this stiffness matrix in case of plane strain. Another case can actually be clubbed into these kinds of situations, and that is the case of axisymmetry. So to understand axisymmetry, we first have to recall a little bit of the coordinate transformations that we did. In the cylindrical polar coordinate system, this operator, the divergence operator or the nabla operator, which is this in the Cartesian system, the operator is epsilon 1 del del x1, epsilon 2 del del x2, and epsilon 3 del del x3 in the Cartesian system. That becomes epsilon r del del r, epsilon theta 1 by r del del theta, and epsilon er del del r, e theta 1 by r del del theta, and e3 del del x3. So this 1 by r del del theta is important, and displacement at a point can be written as this. Here you remember we calculate the strains as gradient of u plus gradient of u transpose. So for the gradient operator we use this, for u we use this, and we remember that er, e theta, e3, all, not e3, er and e theta are functions of theta. They are functions of theta. They are not constant vectors like in the Cartesian system. So we have to take derivatives of them when we do these gradient operations. You must have learned these things in your elasticity courses. So I'm not doing these derivations. Suffices to say again that these are the 6 strain components that you get in the Cartesian system in terms of ur, u theta, and uz. These are the 6 strain components corresponding to the 6 strain components in the XYZ system. Now, in case of axisymmetry, okay, so the equilibrium equation also, this is your gradient operator, which is er del del r plus e theta 1 by r del del theta plus e3 1 by del x3. This is your operator. This is a second order tensor which is written as sigma r er plus sigma r theta e theta and so on. So this is B is a vector again in the r theta z coordinate system. We do these operations. This is a divergence operation with this operator and this quantity, the stress, and then I get the 3 equations of motion for quasi-statics in the cylindrical polar coordinate system. So the point to note is that the vectorial or tensorial physical law remains the same, only its components in the Cartesian system behave differently than its components in the cylindrical polar coordinate system. The actual equation remains the same. So this is just a re-description of this equation. So these are the equations of equilibrium, and these are the strain displacement relationships. Now, in case of axisymmetry, what we assume is that things do not change with theta. See, things do not change with theta, and u theta is almost equal to 0. This is quite like plane strain, where we had assumed del del z is almost equal to 0 and uz is almost equal to 0, but you'll see the effect is slightly different. So these are the strains. These were the strain displacement relationships. So this is 0, this is 0, this is 0, and u theta is also 0. So this is 0, this is 0, and this is 0 as well. So epsilon theta z is completely equal to 0. Epsilon zr is there, and then epsilon theta theta and epsilon r theta. Epsilon r theta is also completely equal to 0. Epsilon theta theta exists. So the 4 components of strain that survive are epsilon rr, epsilon zz, epsilon rz, and epsilon theta theta. So we can treat these three are on the rz plane, and this is out of the rz plane. So we can take, for an axisymmetric body, we can take a plane at any theta, rz plane at any theta, and the situation would be same on any such plane. So once we have done this, once we have reduced the strain displacement relationships based on this assumption, we can now write the constitutive equation in exactly the same way that we did for plane strain and plane stress. We go back to the constitutive equation sigma ij equal to Cij KL epsilon KL, and then we have now only these 4 components of strain, and then we write the 4 components of stress corresponding to it, RR, theta, theta, ZZ, and ZR. These 4 components of stress from the constitutive equation, and we can express it in this form where f and g are functions of nu. F and g are functions of nu. Again, the ordering is important. If you change the ordering, again this matrix will change, but we will stick to this ordering and remark that this also can be incorporated in the same code as plane stress and plane strain. This is just a small tweak, a small if statement. So in case of the axisymmetric problem, we will deal with epsilon rr as epsilon as we deal with epsilon xx in plane stress or strain. Uh, Theta theta we will deal with it as epsilon zz. Zz we will deal with it as epsilon yy in the plane stress plane strain case, and this we will to epsilon zr. So I think there's a 2 here which I have missed. So oh yeah, I think I have to check. I think the 2 is here, but I'll have to check whether this 2 is there. Just I will put it down correctly when I upload the notes. Okay, so here is a small problem. A cylinder which is subjected to a radial pressure. So this is let's say the x is this. So r is this and theta is this. As you can see, the geometry doesn't vary with theta, and the loading also is a pressure loading, so it is also independent of theta. So this is a candidate for axisymmetry. So to do axisymmetry, we have to take RZ plane, any RZ plane. So let's take this RZ plane. So this RZ plane runs from here. So this is the RZ plane on which we can do the analysis, the two-dimensional analysis, and this would look like this. So this is your R axis, this is your Z axis. So it looks like a plane strain or plane stress situation um, in the 2D plane. So it is the ZR plane, you have to remember that. So this in the ZR plane, this pressure would now act from the left, and this is the axisymmetric version of this problem. We can also analyze a plane parallel to the XY plane. So this plane, for example, because this is also very long in the Z direction, so this can also be analyzed in plane strain with the plane strain assumption in this manner. And moreover, since this is symmetric, we can actually analyze only a quarter of this problem, remembering that due to symmetry, this line won't be able to move in this direction and this line won't be able to move in this direction. So we put rollers here, 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 and here to impose the symmetry. And when we do that, we analyze 1/4 of this problem in plane strain, and here we analyze it in axisymmetry. So this is how axisymmetry, plane strain, or plane stress works. You have to use the correct constitutive equation in each case, and if you do that, then you can actually write one single code that can handle all 3 simplified situations.